Hi, and welcome to Mike Likes Robots, where we share knowledge to accelerate robotics. And today is day 23 of the Advent of Code 2024 in Rust. Day 23 is getting pretty close to the end. So today's puzzle was not too difficult to understand, had a bit of trickery to finding the solution. So let's read through the puzzle and I'll show you how I completed it for part 1, and then the same process for part 2. So, day 23, LAN party. As the historians wander around a secure area at Easter Bunny headquarters, you come across posters for a LAN party scheduled for today. Maybe you can find it. You connect to a nearby data link port and download a map of the local network, your puzzle input. The network map provides a list of every connection between two computers. For example, KH-TC is one example, and there's a whole list of them. Each line of text in the network map represents a single connection. The line KH-TC represents a connection between the computer named KH and the computer named TC. Connections aren't directional. TC-KH would mean exactly the same thing. LAN parties typically involve multiplayer games, so maybe you can locate it by finding groups of connected computers. Start by looking for sets of 3 computers where each computer in the set is connected to the other 2 computers. In this example, there are 12 such sets of 3 interconnected computers. Here are the list of possibilities. If the chief historian is here and he's at the LAN party, it would be best to know that right away. You're pretty sure his computer's name starts with T, so consider only sets of 3 computers where at least one computer's name starts with T. That narrows down the list to 7 sets of 3 interconnected computers. You can see here that the T appears anywhere in the list because these are sorted alphabetically. Find all the sets of 3 interconnected computers. How many contain at least one computer with a name that starts with T? Your puzzle answer was 1046. So part A was fairly simple. I immediately thought of one way that I wanted to do this, which was by creating a hash map which mapped the key to all the computers it was connected to, which means that for each line in the puzzle, we're adding 2 entries. One saying that the left computer is connected to the right computer, and one saying that the right computer is connected to the left computer. Then if we ever come across one of these computers again, we add to the entry instead of creating a new entry, which would overwrite it. So we would end up with that TC is connected to KH and WH and any other computers that it comes across. At the same time, KH is connected to TC and QP and any other computers that it comes across. With that, I set out to write the code to do that. So let's take a look. So here is my code. It starts with a LAN party struct, which is that hash map of string to vectors of strings that I was talking about. So KH would be the key, and then TC and WH and so on would be in the vector of strings that it is connected to. I created an enum to allow myself to return an error if there's any problem with parsing the input. And the input parsing is pretty simple. For the line in the puzzle, split by the dash, right? And that's because, let's use test text. KH and TC are joined together by a dash. So the 0th entry and the first entry, or even I'm using iterators here, so match tokens next. If either doesn't exist, then I return dash not found. If I did an index like tokens 0, I don't think I can on an iterator, but if I did that on a vector, it would panic if that entry doesn't exist. So by using the iterator and doing .next, I'm actually able to check whether that entry exists and then return an error if not. If it does exist, then I return a tuple of the left and the right converted to owned strings. Then in the network, I get whether the left has something. If it doesn't, I insert the default entry, which is an empty vector, and then I push the right value. Now I'm cloning here because strings don't implicitly have the copy trait. So if I just used left here, then I wouldn't be able to push it here because it's already used it. The ownership of it has been taken, and you can't implicitly copy. So by explicitly doing a clone, I'm saying take a copy of the left and put it into the network, and then for the right, put the original data. The compiler should figure out that those two operations are the same because I don't change left in order to do that. So it doesn't actually do a copy, but that's up to the compiler to figure out. Okay, so that's puzzle parsing, pretty simple. Let's go on to part A. For part A, I create an empty hash set of all the triples that are in there. And the idea here is that I use a hash set of sorted triples, so that if I do find the same entry multiple times, it won't affect my results. And that would happen if I didn't have that triple and sorting, if I didn't have the hash set and the sorting involved. Then I go over all the keys in the network. For each, I take the value and I check if, first I'm iterating over the same network twice, right? And I need to be comparing the entries. So if I take the 0th entry and then the 0th entry, I need to say, well, they aren't, it's not connected to itself, so just skip it. Then I can get the connections from one of them, the left one, let's say, and I'm using some option matching here so that I can get the vector out because I'm getting it from a hash map where the entry might not exist. If the connections contains the other connection, so if the connections for the left entry contains the right entry, then the original entry is connected to left and right, and the left entry is connected to the right, which means that they must all be connected together because they're all bidirectional bidirectional connections. That means that I can create a triple from the key, the root, and the other. I can sort that so that I don't get duplicate entries where the sorting is different, and then insert that into my triples. From there, all I have to do is check whether it starts with a T anywhere, so anywhere within that triple. If it starts with a T, then I want to keep it, and then I just take the count of that. And if I run that from my main function, I get the result here, 1046. With that, let's go and read through part 2. There are still way too many results to go through them all. You'll have to find the LAN party another way and go there yourself. Since it doesn't seem like any employees are around, you figure they must all be at the LAN party. If that's true, the LAN party will be the largest set of computers that are all connected to each other. That is, for each computer at the LAN party, that computer will have a connection to every other computer at the LAN party. In the above example, the largest set of computers that are all connected together is made up of CO, DE, KA, and TA. In the above example, the largest set of computers that are all connected to each other is made up of CO, DE, KA, and TA. Each computer in this set has a connection to every other computer in the set. You can see the list here. The LAN party posters say that the password to get into the LAN party is the name of every computer at the LAN party sorted alphabetically, then joined together with commas. The people running the LAN party are clearly a bunch of nerds. In this example, the password would be CODEKATA. What is the password to get into the LAN party? Your puzzle answer was, and you can see my answer here. So I did write 2 versions of this algorithm. One is more simple, and I'll talk through that first, because it will lead on to the other algorithm, which is very similar. So for part B, I decided, I was simply going to try and check all of the connections for A. Let's say we have an A is connected to B, C, and D, and then B is connected to A and C is connected to A and B. This is kind of what I thought through. Now, originally, I went with just this setup, which would mean that I take the entries from A and I check that they all connect to each other. So for that, you can do for key and value, check whether, for each entry, get its entries and check that all of the entries in val exist in those entries as well. Something like that. Now the problem is what I just showed, which is that if there is an entry D where D is only connected to A, then A, B, and C are all interconnected, but D is not part of that connection. So going through the val associated with A and getting all of the entries that are associated, means that I'll say, hey, B is completely connected, C is completely connected, but D is not completely connected. So this isn't a good candidate for a full network. But that's not true. So once I realized that was the case, I switched from checking all of the values to checking the power sets of all of the values. Now this is a great function from itertools I've not used before, but essentially what it does is the documentation is excellent for this. So take the range 1 to 4, not including 4, and get its power set. What numbers does it give you? It gives you an empty vector, it gives you 1, 2, and 3. Then it starts giving you all the possible combinations as well. So 1 and 2, 1 and 3, 2 and 3. And also 1, 2, and 3. So in my case, if I took the power set, of B, C, and D, I'd get an empty vector. I'd get B, I'd get C, I'd get D. I'd get BC, BD, and CD, and I'd get BCD. Now, this entry would show that it's not completely connected. CD would show it's not completely connected, BD would show it's not completely connected, and BC would show that it is completely connected. I would throw away B and C and D because they're not actually long enough. They're not at least 3 interconnections, so they're just not going to be the biggest. And I could assume that based on part 1. So based on that, I go through all the keys and values in my network. For each value, I take its power set, and then I check the length of that power set, and if it's less than 2, I discard it, because that would give me less than a triple, and there's no point in checking it. Then for each of those, I go through, I check for the root and the other. If they're not the same, then continue. Otherwise, check if the other is contained within the roots network as well. As the comment says, if you've got to here, then the network is okay, add it. And that's because this continue continues this for loop to go to the next other, and this continue continues the outer loop, which is labeled here. It means this network does not match, move on to the next candidate network. So if we get to here, neither of those continues have fired, or we've gotten to the end of the network, at which point I want to add all of the candidate network in. So I do a vector containing the key, and I chain together the candidate network and pull it all together into one vector, which I sort and insert into the hash set, same as in part A. Then from that, I iterate over the complete hash set once it's built. I map a network to a tuple of the network and its length. Then I use a maxby function, which says sort it based on the length of the network only. That's what this key is. Take the left's length and the right's length and do left compare right. Then I can map that. So given a network and a length that I no longer care about, because I've gotten maxby, right? I can join it together with a comma and return it. Now I can run this. And it does work, but the problem is, as you can see here, the amount of time it takes to finish going through all the targets. So it does take maybe 4 or 5 seconds. I figured there was a better way, and after thinking about it for a bit, when I say a different algorithm, it's more like an optimization for the same algorithm, which is that instead of pulling together a hash set of all the possible full networks, instead of that, I only track the lengths of the largest networks, or even just I only track the longest network that there is. So for the key and the value in the network, I do the same thing. I'm iterating through the power set, only this time I'm only checking it if it's at least as big as my biggest network so far. So it starts out with a biggest network of 0. So 2.max, I want it to be at least a triple. If the candidate network length is less than 2, then continue, because at this point biggest net has a length 0. So 2 maximum with 0, even saturating sub 1, will still give me 2. So I'm ignoring it if it's less than a triple. The rest of this is the same, except that I'm storing the network instead of pushing it into a hash set. I'm storing the whole network. So instead of, I build the full net, and instead of inserting it into full networks, I just overwrite biggest net with that network. Now the next time round, let's say we've already got one of size 3. This is where it gets more interesting. Now biggest net is of size 3, and I need to check whether it is less than that amount. So 3, saturating sub 1, and saturating sub will subtract 1, but it will stop at the lowest possible number for that data type. In this case, I'm using length, which gives it a U size, which means it will stop at 0. So 0 minus 1 will still give 0 if you're using saturating sub. That's why that's in. Once the biggest network has a length of 1 or more, it's essentially just the length minus 1. So say we've got 3, 3 minus 1 is 2, and then 2 max with 2 gives 2. So now we're checking that the candidate network has a length. If its length is less than 2, meaning we'll only get a triple out of it, then ignore it. And the reason for this saturating sub is because the key here is not being included in this candidate network number, right? So candidate network dot length plus 1 for the key is its actual network length. So we solve that by doing a sub 1. Now, next time round, we get a candidate network that's 5, and we've stored it. So now we're going to take that. 5 minus 1 is 4. Now we want to check whether the next candidate network is more or less than 4. Because 2 max with 4 is 4. So then we're ignoring all the triples and all the quads that we get from then on, which means we're checking far fewer networks. And that's essentially all that's different about it. We're just ignoring networks with a length that's lower than our largest current network. Then at the end, we don't have to iterate over a hash set because we don't have a hash set, we just have the network itself. So we iterate over it and join it with a comma. So this time, I'll run it with part B so you can see the difference in time. So let's run it. It's running, and it does take a few seconds, 4 to 5 seconds. And there it is. The second part B took less than half a second, I would say. So just with that optimization, I'm comfortable that I've solved this problem in, if not the best way, at least a very good way. And there's also some unit test functions down here that check all of the input parameters, or all of the test cases that the puzzle gives. With that, day 23 is complete with the fully correct answers. Thank you for watching, and I'll see you next video for day 24.